Hello, everyone. This is Gordon Rosner, president of the East Valley Astronomy Club. Welcome to our online September meeting. And up on the screen, you can see our agenda. It'll be a welcome, introductions as usual, club news as usual. Member presentation will be by me this time. We have a special presentation this time. We're fortunate enough to have Rick Alling. I spelled his name wrong. Sorry about that. It's actually
pronounced exactly right.
Yeah, from ASU. And then when we have our featured speaker, Roger Windhorst, about the James Webb Space Telescope. So welcome, everyone. I hope everyone lives long and prospers. Introductions. Here is your leadership team, as usual. I always throw this slide up so everybody remembers who their leadership team is. Little difference this time. See the orange names, and then down at the bottom, it says these office term limits expire this year. So those in orange, president, vice president, treasurer, their terms by our Constitution and bylaws expire by the end of this year. So next month, you'll be hearing a lot about elections, how we're going to do it during these special times, things like that. But just getting everybody to know that by the books, these people's term limits are expiring this year. Club news. As usual, all EVAC personal contact events remain canceled, just like the last few months. Basically, everything that we get together formally, face-to-face, is still canceled. Still don't know when that's going to change. Member presentations. If anyone would like to do one, please let me know. They last about 10 minutes or so, and whatever subject the member would like to tell everybody else about. Like, for instance, tonight, I've got a lot of requests about astrophotography, about starting completely from the beginning. So I thought, okay, I'll give one. I'll give a kind of a first level one. So if anyone wants to give a member presentation about anything, let me know. Get in contact with me. And remember that the Hovado Airfield is not available for events. And I've been getting suggestions from people about new sites. Please keep them coming on in. In fact, people are using our Facebook page to make suggestions. We haven't decided yet. We don't have a short list developed yet, but we definitely need to find something. So keep those cards and letters coming in. Remember that these monthly meetings are being recorded, and a link will be provided on our EVAC website. So if you know of anyone who missed the meeting, go into our website and it'll be on there. So the next EVAC meeting is on Friday, the 23rd of October. This is the fourth Friday. So the 23rd of October is the fourth Friday. We normally do this on the third Friday, but this time it's the fourth Friday because about a year ago when we set up our schedules, this third Friday would have been the weekend of the All Arizona Star Party. So our calendars have always been saying the fourth Friday for October, and we wanted to keep it like that because people probably put it on their calendars and they're ready for it, and we don't want to change things again. So we're keeping it on the fourth Friday. And our October meetings, main presentation will be Anthony Wesley about high resolution planetary imaging. So member presentation, me. And let's see, Tom and Roger, can you unvideo yourself?
Okay.
Video or unvideo? We were unvideoed.
Yeah, unvideo yourself.
Oh, like that?
Yeah.
Okay.
So Tom, who can you just see me as a?
Yeah, I just see you, Gordon.
Okay, good. Now it's working. It's probably the issue is on my end. All right, so this is about beginning astrophotography. This is the most very basic presentation on beginning astrophotography. I mean, this is something that if you just walked in the door and someone mentioned astrophotography and you don't know what it's about or how to get started, this is the presentation this time. So you always have to take a couple steps back to make a leap forward, right? And oh my gosh, this guy certainly took a leap forward, didn't he? And these guys look like they're having fun. It looks like in skydiving, we got two guys linked up and there's probably a formation that's building. But why am I showing old skydiving pictures in an astrophotography presentation? Well, freefall photography combines two very different activities, skydiving and incorporating a camera. Astrophotography also combines two very different activities, observing the universe with a telescope and incorporating a camera. So even though astronomy and skydiving seems worlds apart, really it's an activity, both are activities in which cameras are incorporated in very specific environments. So, all right, both require understanding your camera and adapting it to a unique situation. Both of those give some very exciting pictures. And check out this one. These three guys in free fall, 120 miles per hour, heading towards the Earth, having one good time. And then look down there at the lower right. Okay, astrophotography. Show this around to your friends if you take these pictures. So even though totally different, they are quite fun to do and quite fun to show. Wow, is that really me back in 1975? Yep, and I took those skydiving pictures with a helmet-mounted camera, the Minolta XG7, had an electric motor drive and a remote release. And yep, that's a film camera. Remember, it was back in 1975, and I still have that right here. So this is up on my shelf. This is a good remembrance of incorporating a camera into a very strange and unique situation. So here's my point. You know, looking back, one of the most memorable times of my life was figuring out how to mount that camera, learn about the camera, and incorporating it into my skydiving passion at the time. So this presentation is about the first steps in incorporating a camera into your passion, which is astronomy. It will be very rewarding and memorable also. So let's get at it. What telescope do you have? Hopefully you have one, but some people may not have one yet. And they want to get into astrophotography, but they don't have a telescope yet. They're scratching their heads. What should I get? Well, there's a reflector up there at the top. It uses mirrors. The refractor uses lenses. And catadioptric uses both of them, basically. And those are the Schmidt-Cassegrains and Maksutofs and other ones. So those are the three basic types of telescope, but which type is best for beginning astrophotography? Boy, that's difficult to answer. They all work, but in general, a small, wide field refractor, like this one, that'll accept 2-inch eyepieces, works best for beginners if you're only going to have one telescope. This really suggests 2 inches because with 2 inches, you can adapt it down to 1.5 inches, but 1.5 inches, you really can't adapt it up to a 2-inch. So a 2-inch will allow you to grow in the future. So that was a nice first, doesn't have to be a stellar view. There's a nice little one, easy to transport outside and hook a camera up, which we'll get into. However, there's always a however. One type can be very difficult to use for astrophotography, and unfortunately, it's the most popular one out there, and that's the Newtonian. And you can see the one on the right, the SkyQuest, the Dobsonian telescope, which is a Newtonian on a Dobsonian mount. Very, very popular, comes in different sizes. I have 2 of them. But why are these so difficult? Doable, but very difficult. So let's look at the light path of the three different types of telescopes. Here's a light coming through the refractor, which is just uses lenses. So it comes on in, bounces off a little mirror back here. You don't have to have that diagonal, but in this case it does. And then that mirror comes up to a little point, that light path, right? Comes up to that little point. And then the reflecting telescope mirror bounces around, but it comes back to this little point right there. And the kadioptric bounces around, comes back to this little point right there, and you can see it kind of magnified right there. Look, this comes to a little point right there where it's focused down. So let's look a little closer here. The telescope focal length is how the telescope is bending the light into a focus point, right? Regardless of whether it's a reflector or refractor, it's taking the light from the objective lens and bending it into a focus point. And then the eyepiece, what the eyepiece is doing is it is bending the light also to focus on that point. And then that's what you see. And by the way, the exit pupil is, this is what an exit pupil is called where it's at right there. Some people call it an eye relief. So let's look closer here. The eyepiece focal length. This is the telescope's focal length. This is the eyepiece's focal length. So let's focus on here. So to focus a telescope with an eyepiece, you have to bring the focus points, the two focus points together. So here's the telescope. It comes up to a point. Here's the eyepiece, and that comes down to a point. And then your view is very sharp. Now, the eyepieces, depending on what magnification they have, this length will change depending on the little number on the side of the eyepiece. At 11, 40, 17. So it changes this length in here. So if this length changes, well, obviously you've got to change the location of the eyepiece. So this is why whenever you change an eyepiece, you have to refocus, because that eyepiece focal length has changed and you got to refocus it to get it down to that point. To focus a mounted camera, now the camera has a sensor. So you want to get that sensor down to that point where the telescope focus is. So the sensor needs to be there. Well, for a Newtonian, the camera must move in close. And most of the time there's not enough room. So this is off of a reflector, a Newtonian. You can see this is the focuser, and then here's the secondary mirror. All right, so I took this off of a telescope. So that focus point is, let's say, about right there in the middle of this focusing body. No big deal. We have an eyepiece, and it can focus in and bring its focus point to that point right there. Now imagine you take the eyepiece off and you put a camera on there, and the camera focus is right there. There is its sensor. So the camera has to move forward. It has to move further on down. And if the telescope's point is right there, there's not enough room. The camera bottoms out on the housing. So you're stuck. You can never get it in focus. So that's a major problem with the Newtonian. There's just not enough room to move it on down. But there are a few suggestions. And number one is you take your telescope and you remove the primary mirror and you move it further up the tube. That brings that focus point further on out. Right? Now, it sounds like a major thing to do, and it can be, but it's basically not very difficult. I happen to take this one out of a telescope that I had that I rarely use, and there's just generally 3 bolts. You undo them, it slides out, and there you have this in your hand. And you can either cut the tube, which you have to be pretty precise, so you need to have a lathe or a mill or something like that. Drill the holes, put this back on. A little bit of math involved as you try to figure out how far you want it. And you bolt it back on and you're set. Or here are the adjustment points. You can see the spring, right, with the screw. As you get longer screws and longer springs, and that'll pull that mirror further in, and then you don't have to recut or remount the mirror assembly itself. So it's doable, and some people have done that. They have an old Newtonian, and he says, just sitting in my closet, I think I'll experiment around. I think I'll cut one down, move it up, and then, hey, I've got a nice little astrograph dedicated for taking pictures. So it's doable. But then it's not very usable visually because now you got that focus point way, way, way on out there. And it can be a little difficult to focus eyepieces in. Or what you can do is you can replace the focuser assembly. This is the focuser assembly that I showed you earlier. They make them that are low profile. So, you know, they're only like an inch tall. And you can just reinstall that. Generally have to drill holes to mount it. But that's an option. Sometimes that low profile focuser can be more expensive than the telescope. So keep that in mind. But there's always an easy solution. You add a Barlow lens. And remember these things, generally everybody has a Barlow lens somewhere, at least one rattling around in some box somewhere. Most people don't even know what they're for, but they usually come with a telescope and come with kits. So search around, get that Barlow lens, put it in as an eyepiece, and then attach the camera to it. Because this Barlow lens, as you can see down here, this is the normal light path, which normally would come to a point here at A. That's deep down in a normal focuser. It now bends the light and makes the focal point longer out here to like B. Now you've got it out where it's further on up. And then you can put the camera on and the camera sensor is right there at the image point. So if you're interested in turning your Newtonian into an astrograph, try that. Dig out that Barlow and use it. There are some Newtonian telescopes designed for astrophotography. They have that focus point further on out, so a camera can easily attach. They're called Newtonian Astrographs, and they work very well. Plus, you can use them visually, but then you have to have some adapters because the eyepiece has to be so far out now. But they work very well. But you have to specifically get a Newtonian astrograph. What about the refractors and Cadiatrics? Mention those. These have telescope focal points further out. So go back to ours, and in this case, these types of telescopes, the focus point is further on out, okay? And they usually have a lot of focus travel. Look how much travel this refractor has. Check that out. So chances are you can get that focused in on you. However, everything has a problem. With every good comes a bad. The telescope focus point may be too far out and you don't have enough. No problem, because they make these very inexpensive little kits that you just sort of stack between the telescope and the camera. And I mean, you can get an entire kit here, all different sizes, for maybe $30. And what you do is you stack them up in front of the camera, and then that will bring it on out to the focus point. Or you can try to, before you buy anything, is stick your diagonal in there, because the diagonal gives you a little bit more distance to play around with. Diagonal, well, it's a mirror, and you really don't want to have mirrors when you're doing, or you want to not have a lot of mirrors when you're doing astrophotography. But, you know, something to start with, play around, get a focus going. So what cameras are available? Well, there's a smartphone, there's point and shoot, DSLR, and a dedicated astro camera. Which camera is best for the beginner? Well, let's take a look at each one. The smartphone, we all know about that. It has a camera in it. Very difficult to use, very difficult to focus on up. It's an autofocus. Sometimes it tries to focus on the lens or the floor, and it's difficult. And there's just no versatility with it. You have to take about 50 pictures to get a good one, but you get a picture. Point and shoot. These were popular a few years back, before the cell phones became popular. And these might be laying around in a drawer somewhere. And they're a very nice step up, and they work pretty well. It does have some limited versatility as far as setting exposure times. So if you have one of these around, good thing to use, good step up. The DSLR, yeah, man, most common one. This is what actually we would want to use. We want to strive for as a beginner astrophotographer. The dedicated astro cameras, like the ZWOs, these things that can be up into the thousands of dollars. Best to move up to those later. They need a computer and software to operate. Some of that software is very complicated and can be quite frustrating at first. So how do I attach the camera? Well, let's take a look. The smartphone and the point and shoot, they're both the same. You just can't sort of clamp them. And here is my little reflector, my little Newtonian. And here is the point and shoot right there. And there's this object right here that has knobs and it has adjustments. And all it does is it clips on to where the eyepiece is. That holds it steady. And then you can take pictures from there, right? So it just clamps on. There's a screw up here that clamps on. So both the smartphone and the point and shoot just clamp to the eyepiece. Then you get to play around. Both of them, not all that much versatility. It's sort of you press the button, you got a picture, and that's all you're really going to get. The DSLR, digital single lens reflex. I talked a little bit about this at the end of last month's meeting. This is the way to go. Because it's so versatile, you can control exposures, ISO, has histograms on it. A lot of features inside here that you can control the camera. This is what is fun about astrophotography, is all the things that you can do with this camera. What I recommend, if you're going to go out and buy a used one, this is an old one, this is probably 10 years old, it's Canon Rebel, is a flip screen back here. And this turns, right? And so the idea is if this camera happens to be pointing down as you shoot something straight up, you're going to be laying on your back or whatever trying to look at it. Whereas this, the screen flips out, turn it around, and there you're looking at it right there. So highly recommend, if you're going to go out and buy a digital camera, is get one with one of these flip screens. You'll be happy that you did. Dedicated astro camera, they need a computer. This happens to be a Malin cam. This one has a function where it will go directly to a TV screen monitor. But to control them, you really need to go through a computer. Same thing here. You need to go through a computer. However, you just take the cap off, and they just fit right on where your eyepiece would be. No type of special adapters or anything needed. They're made to slip on to a telescope where an eyepiece would go. So now you have a camera, you have one of those, and it's attached to your telescope. Excellent. Now what are you going to do? All right, here's the big screen. Just start taking pictures. Assuming you have are using a DSLR, and I hope you start out with that. Experiment during the day. Oh, don't look at the sun. Avoid the sun. As a matter of fact, I tell people to get underneath the patio. If you're using a telescope during the day, if you're experimenting, get under a patio, get in the shade so you don't mistakenly swing it around, pointing at the sun. Pick some faraway object like a hilltop antenna, a telephone pole, something out there. Now this is during the day. You can see what's going on. You can play with the adjustments. Right? Understand your camera's manual mode functions, ISO settings. the histogram. You can understand, you can play things with things a lot better in the day rather than in the dark of night. Then once you get comfortable with your camera is move to night operations. Usually at night you will stay under 15 seconds. Anything longer than that, and you just start getting things blown out. Generally under 15 seconds. Some may be able to go up to a minute without any kind of special guiding. Start with the moon. The moon's a great target. You can also take pictures of the moon during the day too, because it's out during the day, right? It's an easy target. You'll be using exposures way under 1 second. Basically, you can put the camera in auto mode and it'll pick out a pretty close exposure, but play around with it. Play around with exposures, with the focusing, with the ISO. Look at what the histograms saying. Get familiar with your camera because you'll be using it a lot. A lot of time will be spent at night doing this hobby. You'll be using high ISO settings. So, 1600, something like that. Not the lower ones, but generally higher ones at night. Got to watch out because the higher the ISO, the more noise you get in the picture. So try to play around with the lower side of the high side, the lower side of the high side. You'll be using high ISOs, right? It would be advantageous to get a remote camera release. So one of these. What this is it just plugs into the camera to the DSLR. The button here will allow you to release, get the exposure going without touching the camera. Because as soon as you touch the camera, it jiggles just a little bit and it's starting to take a picture. So you press a button on the camera and it jiggles and then it settles down. Well, your picture is going to see that little jiggle at the first. Whereas this, you're not touching the camera, you're just pressing this button. So document your settings. You're out there and you're learning things and, oh, this setting is great. This setting is not any good. I like this one, so I'm going to write down what they all are. Because you go out there tomorrow night and you'll forget what all the settings are. Jot them down. Oh, this works. This doesn't work. I need to do this a few more times. So document your settings. Start making mistakes and learn from them. People will learn more from their mistakes than they will from their successes. So go out there and start making mistakes. Do your research. Look around the website, Cloudy Nights. There's YouTube channels. I really recommend Astro Backyard and The Lazy Greek. Both of them very good. Check out a Facebook page. Try to get together with them to kind of get into software, Photoshop, Backyard EOS. And here's a DSLR mounted on a 10-inch Schmidt. And this is just single little clicks. There's Saturn, the moon. No processing, no stacking. Here's what the Orion Nebula looks like, as if you were looking through a 10-inch eyepiece. And here's what it is with a DSLR. Single shot, 15 seconds. One exposure, 15 seconds. No stacking, no processing. And look what you end up. So now, go out there and start your adventure. And remember, it'll always clear up in a few minutes. Okay, that's mine. And next up is Tom, our vice president, who will present our next speakers.
Thanks, Gordon. That was very useful. A nice summary of beginning astrophotography.
Oh, good, thanks.
Next up, we'll have Rick Elling. ASU's Observe the Moon Day. I think Rick has a program involved and needs the help of some of us out here listening today. So I'll turn it over to Rick.
Hey, thank you, Tom, for inviting me to come tonight, and thank you, Gordon. That was a great presentation. So wonderful. What I like to just sort of, I just have a quick little spiel, and I'd like to sort of invite people to sort of maybe get involved with us in a little project. Unfortunately, it's very soon. It's next weekend, and so I don't know if you know already or not, but every year there is a day dedicated to observing the moon. International Observe the Moon Night is what they call that, and typically during sort of non-COVID times, one of our centers on campus, you might be familiar with it, the Lunar Reconnaissance Orbiting or Orbiter Camera headquarters. They have some students, they set up some telescopes outside, and there's many college-age students kind of wandering around the grounds, and they come and sort of observe the moon really through a telescope for maybe the first time. They're not doing anything this year because of the COVID, and I saw, Gordon, as you sort of started your presentation today, I saw in your announcements how much stuff is not going on, right? We're not visiting together. We're not having little crowds. We're not sort of like, you know, having our regular group meetings. And so we have been experimenting with different ways to get out virtually into the community. And one of the things we've been doing is every other Wednesday night, we have a virtual night sky program. I had one 2 days ago, right? That was Wednesday. And we're just kind of taking a piece of the sky. We're talking a little bit about history, some culture, some things about the night sky. And we've developed quite a little audience as we sort of now have a mailing list of 500 or 600, generally, you know, somewhere between 250 and 300 people are visiting us every Wednesday night. I had the idea of actually sort of like doing something for the Observe the Moon Night. And so what I'm specifically asking you about, because I think if I go to an astronomical club like you are, we're trying to find some people that have the equipment and the technology and the know-how to just rig a camera to their telescope and broadcast it. Just get it attached to your computer. You can share that with me in a webinar format, and we can just see what you're looking at. And so the plan is, I'm gonna go into chat here real quick in just a moment. I'm gonna give you my email address. And if there's anybody in the club that would like to do that, if you know somebody that sort of has that technology and would like to participate in this night, it's next Saturday, September the 26th. And so and so that's really my appeal. So I'm trying to locate, if I could get 4, 5, 6, 7, 8 participants from around the valley, have different equipment, different kinds of technology, but the ability to sort of show the moon and share it on a screen in a computer format. I will launch the webinar. I'm going to be the host, and we'll sort of like just go kind of telescope to telescope and look at what we're seeing. I will interview the sharers, right, sort of for what you are and who you're associated with and what part of the valley you're in, and why you're interested in astronomy in the first place. And that's really the plan. So that is my spiel. That's all there is to it. I'm going to have to launch this and announce it probably on Monday or Tuesday coming up next week in order to get enough audience and sort of to get enough interest. But I'd like to know that there are some people that that might like to do this particular kind of project with us and see where we go. So I'm going to stop there. If there's any questions or if there's any way to ask a question, this would be a good time to do that. And I will, so I'm just going to put my email address in the chat right now. So if that is something that you guys would like to participate in, let's do that.
So
Rick,
what time of day are you looking at?
I'm talking about doing this between 7:30 and it's kind of open-ended. So I think what we will do is launch the webinar at 7:30. I note that the moon next Saturday is a waxing gibbous, so it's about, I would guess, about 80% full. That gives us a little bit of a terminus. So if we have some focal length that is showing us parts of the moon instead of the whole moon, that would be really cool to look at some of the mountains and the valleys and that kind of thing. Also, if the night goes well, it doesn't have to be limited to the moon. I think we have to start and end there, but Jupiter and Saturn are right next to the moon. So if we have an opportunity to swing over, if somebody wants to sort of like show us something else about one of those planets that's right up there, I think it'll be great. And so what our project is, the reason we're trying to stay in front of people and trying to sort of like make the COVID into something where we can be virtual and be into people's houses, is to get people outside and sort of get them thinking about the world around them. I mean, we're all locked in right now. And so I've been really enjoying this idea where I show them something in a presentation. Here, go look at this. And then I close down my presentation. I have no idea what the participants are going to do, but I'm hoping that they're walking out in their front or backyard and just looking up at the sky and seeing what we're talking about. And this is really what we're trying to do next Saturday. So if you can, if you want to, if you have the technology, if you want to participate, please just email me. We'll get a handful of panelists that have the technology to show the moon, and then we'll go about the business of just getting this out to a bigger community and see how many audience we can come participate. So thank you for that. Thank you, Tom, for allowing me to make my spiel tonight. Thank you.
All right, thanks, Rick. That sounds like a great opportunity for everyone to get involved.
Excellent, good job, and enjoy Roger Windhorst. I've run into him once or twice in my running around, and I think he's an amazing speaker. So this will be good. All right, bye.
Okay, thanks, Rick. Okay, now it's my honor to introduce our featured speaker tonight, Professor Roger Windhorst. And before joining ASU in 1987, his research focused on radio astronomy, where he studied the cosmic evolution of radio sources and conducted systematic radio surveys. Then, after being at ASU for a few years, Roger was named a Regents Professor, which is the highest honor ASU bestows upon professors for distinguished accomplishments such as pioneering work, publications in first-ranked journals, critical acclaim by their peers, and important contribution in teaching and public service. In addition to having over 200 published refereed papers, Roger has brought in millions of dollars for over hundreds of research projects, including recently 2 large grants for the Hubble Space Telescope and the James Webb Space Telescope for fiscal years 2020 to 2025. So very recent and projects coming up. And Roger's been involved with over 50 Hubble Space Telescope projects, was a key member of the Oversight Committee in the design of the Hubble Space Telescope Wide Field Camera 3 from 1998 until the launch in 2009. And he's currently leading the Hubble Space Telescope archival legacy project called SkySurf, which will examine over 60,000 Hubble Space Telescope exposures to accurately measure things such as zodiacal belt brightness, faint Kuiper belt object populations, and the extragalactic background light. And SkySurf will set limits on the diffuse extragalactic background light, which will constrain the formation of galaxies since the epoch of cosmic dawn, which started somewhere around 1 billion years after the Big Bang. And he's also one of 6 interdisciplinary scientists worldwide for NASA's James Webb Space Telescope, and an active member of the James Webb Space Telescope Flight Science Working Group. And Roger's here today to tell us more about the James Webb Space Telescope. So take it away, Roger.
Thank you very much, Tom. Let's see if I can get the screen share to work here. Might as well share everything just in case I need to call on a video. I do in fact have a, oops, that wasn't very successful. I should have gone straight to the top here. I have too many slides, which I will simply solve by not talking about all of them. And some slides will go pretty quickly. So I appreciate you having me here. I agreed with Tom, since I have only moderately good internet connection and my laptop is overheating, that should the laptop or the internet fail, he has a copy of the PDF file and I will dial in then by phone into the meeting. Let's hope that that wouldn't be necessary. But we're NASA, so we always have a backup plan. So I'm going to talk about first light, galaxy assembly, supermassive black hole growth with Hubble, Webb, and for good record, I'll toss in a few other future telescopes. So to the left, we have the Hubble Space Telescope here. It was first funded by Congress in 1973. I don't know where most of the audience was in 1973. I think Rick Allen was around, maybe Tom, but I just got out of high school. And Hubble is still operating after 30 years. We'll see more details in a minute. And we have a few more years to go with Hubble. James Webb, can you see my cursor here?
Yes, that's visible.
Yeah, okay. Was first conceived in 1996 and will be launched next year and should run for at least 5 years, hopefully 10 years. And then in the early 2000s, the next generation ground-based telescopes was conceived, the Giant Magellan Telescope that ASU is part of. And they should run for many, many decades when that becomes operational later this decade. And then for the young folks in the audience, including the high school student, Miss Matthews, I want you to start thinking about what comes after Hubble and James Webb. And that would be this, this thing to the right here called the ATLAST, or the Advanced Technology Large Area Space Telescope. That hasn't been funded by Congress yet. There's a large number of people in my research group. I list some names here. The list is not complete. There are some other students in the audience. Welcome to everybody. And here's where we get going. So thanks again for inviting me. I have talked about some of these topics in the past. I believe it was more than 3 or 4 years ago that it was at EVAC. So I'll give you an update on the James Webb Space Telescope where it stands today. That would be 2020. And then I'll give you a brief review of what Hubble has done in terms of galaxy assembly and supermassive black hole growth. And by the way, Tom, I should say, I also regret that we don't meet in person for many reasons. It's always good to talk to people. I also miss the break time where you have these excellent cookies and junk food. So perhaps we should have a 5-minute break in the middle if I am going too long, but please give me a warning. Also warn me, since I cannot see the chat as we go, if there's any questions in the chat, okay? And then third, we'll talk about how the Webb telescope can measure the epoch of first light, galaxy assembly, supermassive black hole growth. And as I said last, we will talk about these next generation telescopes. I'll have some conclusions. I have a couple of extra topics in there that we'll probably won't go into unless you have questions about it. Like, what is the update of the programmatics of JWST as of today? Are we really going to launch on time this time around? It has been postponed so many times, and so on. I have a little more on star formation and exoplanets, and a couple of charts or where our students end up. And I have a link to the talk here at the bottom in case you want to get the PDF file. So my first chart. I got this at Caltech when I was a postdoc there in 1986. Jim Westphal's office at Hine on the Wall, and he gave it to me. And he had obviously written this for the Hubble Space Telescope. It's like a hot bath. It feels good while you're in it, but the longer you stay, the more wrinkled you get. And so Hubble has been a project that's almost gone on for half a century. I want you to let this sink in for a minute. And the James Webb Space Telescope has gone on for more than 20 years and will be more than 30 years by the time it's all said and done. So we're looking for new young folks who can take over from here. All right, and that's one of the goals of this talk, is to make the young generation enthusiastic about space astronomy so they can design the future instruments. So on the left, we have Hubble the astronomer, who discovered the expansion of the universe in 1929. And the Hubble Space Telescope was named after him, as I said, conceived first in the 1970s. Actually, that's not quite correct. It was first conceived in 1946 by Lyman Spitzer, who wanted to confiscate a German V2 rocket and put a small telescope on it. Well, that didn't quite happen that way. They had some other orbital missions in the 60s and 70s after Sputnik, but the first space telescope that was launched of any size that was Hubble, that was not launched in 1990. It took 17 years to make from start to launch. And as I said, we have another number of years to go, although the telescope is aging. And then James Webb was conceived 20 years ago and will be launching in October next year and hopefully run for a decade. The telescope is named after this fellow here, who is standing next to JFK. He was the second NASA administrator. Jim Webb, and he stood up to Kennedy when Kennedy said, you know, there was a conversation in the White House that was taped. The tapes have been released. Kennedy used a 4-letter word. I can't say that here, but he said, you know, I don't care. Don't give this word about going to the moon. I just want to beat the Russians. And then Mr. Webb said, no, Mr. President, if we go to the moon, we have to find out what's there. So Mr. Webb invented space science, and that's why this telescope is named after him. So the Hubble Space Telescope is slightly larger than a human being, 2.4 meters in diameter with a central hole. The Webb telescope has an edge-to-edge diameter of 6.5 meters, so it's 2.5 times larger. And it works also at longer wavelengths, so it will have the same resolution as Hubble has in the optical, in near-infrared wavelengths, or it will have better resolution in the wavelength range where it overlaps with Hubble. It's a completely new, different technology, these 18 hexagonal segments. So to the left here, you see the copy of a book, not written by James Webb, the NASA administrator, but Jim Webb, the senator of Virginia, who was quite helpful to help us restore the project when we went over budget by a factor of 2 the first time around. That was in 2010, 2011. You see here the Northrop Grumman prime contractor's traveling copy of the Webb telescope. This is not a real thing we launched. It got bird droppings on it, but you see it here in front of the US Capitol, and you can see there is almost nothing standing in the way between the James Webb Space Telescope and Congress now, except for some military spending over here. I say that with tongue-in-cheek and with gratefulness, because various branches of the government feed technology to each other, and the James Webb Space Telescope has also benefited from that. So these things are not coincidence. By the way, we are looking for lots of students, including high school students, that can help us work on this data. We don't want you to die for the Webb project, but it will be worth fighting for. So let's get to the telescope itself. How much time do we have? Tom, I know we run a little late with the other topics. Is there time for a 3-minute movie?
Oh, sure. Yeah.
Yeah, okay. And if people need to leave, I understand, or you give me a holler. I can stop at various locations or skip a few slides. So let's see, you're not interested in my email. If I can figure out how to, I'm not interested in my email either. So here is a YouTube, and yell, Tom, if you can't see that, of the folded up, the solar panels to the side, or the Sunshield to the side, and some of the mirrors folded backwards. And I'm going to play that. You can Google for it on YouTube. The first thing that comes out after launch is the solar array. And then the high gain antenna comes out. And then they pitch the telescope by a couple of degrees so that with the thrusters, they can make mid-course correction burn that lasts for a couple of minutes to make sure they make it, as we'll see in a minute, past the orbit of the moon. And it will pitch back in dark space to let the high gain antenna come out and let it point at the Earth. And then they do another mid-course correction. And then they pitch it again, and they bring these big garage door size pallets, as we call them, a unified pallet structure down where the Sunshield rests upon. And there's one on each side of the telescope, and they fold up and down. And this has been tested with the real hardware in the chamber, as you will see. So this comes out, and this is all at movie speed. It takes about 30 days to do all this. So it's like watching grass grow. It's very slow, and it's all done in one graphic. Then there's a mechanism that pushes up the telescope by about 1 meter, so it hangs above the Sunshield. You need to do that before you deploy the Sunshield. Then the Sunshield covers roll off. I can't tell you how that's done. That's proprietary, but it's very clever. And then along these 6 vertical spreader bars that come in pairs, they're gonna deploy the Sunshield. But first, part to the side comes out, like the sides of an airplane wing, a delta wing, on both sides, telescopic motion that pulls out the sides of the Sunshield. That panel you see a fold here is not a solar array, but it's a heat exhaust panel, a radiator. And then along these vertical 6 fingers, the 5 layers of Kapton will move out by about 1 meter in total. And each layer reduces the ambient temperature about a factor of 1.5. That mud flap that's unfolding here is an angular momentum device. I'll talk about that later if we have time. Below the Sunshield then, there's more radiators folding out, is the spacecraft with all the electronics. And then finally, last but not least, when all the radiators are deployed and the electrical system is alive, the telescope unfolds. First, the secondary mirror comes out on this mechanical arm over the head of the telescope and folds into place with a redundant mechanism. And then the 2 panels of side mirrors come out from the side and fold forward. So you have 18 mirrors that at that point, more or less in focus, not quite. I have a lot more detail on this, but we'll leave it at that. And be happy to take a question at this stage. Otherwise, we'll continue with the real talk. Let's see where the talk is. So when it's deployed, it looks like this. And this obviously needs to be fabricated on the ground and tested on the ground many times in 1 gravity. And then it needs to work flawlessly in space. So the total diameter is 6.5 meters, as I said. The effective area is 25 square meters. So it's an infrared telescope for both imaging and spectroscopy between optical visual 0.6 microns and 28 or 29 microns. Launch date is next month, next year. In 13 months, we go up in the air on Halloween, if you believe it or not. And so this array of sun shields keeps us cool from basically room temperature, 300 Kelvin here on the bottom side. The sun will always be at the bottom in this drawing. And the dark side is always on the top where you get down to 40 Kelvins. Of course, after collecting micrometeorites for 10 years, the Sunshield, which is 40 Kelvin on the dark side, will have lots of holes in it. Because micrometeorites typically come in at orbital speed of 30 kilometers a second or 40 kilometers a second, and they will create tiny holes. So the Sunshield at that point will look like a Texas road sign. It's designed to do that. There will be some additional stray light from that, but it is what it is. And so when we sit like the folded up bat in the launch fairing of the Ariane 5, this is a European, US, Canadian project. We are the lead, but Europeans provide the rocket and 2 of the scientific instruments, and the Canadians provide the guiding system. In a couple of minutes, we'll make it to orbit across the Atlantic. And then over Africa and India, we will start deploying. First, we throw off the launch fairing, and then the sequence you just saw will take place. There is something important to remember, which you may recall from the astronaut servicing missions. When you go around the Earth, if my mouse was the Earth, and you go around every 96 minutes, like Hubble does 15 times a day, you have 15 sunrises and 15 sunsets a day. That's very tiring, not only for the astronauts, but also for the telescope. It causes focus changes, or metal fatigue, this and that. You go between room temperature and minus 100 centigrades every 96 minutes. When Webb gets launched, it will have 1 sunrise, that is when the launch fairing opens, and 1 sunset a couple of days later when the Sunshield deploys. We're under the launch weight of 6,500 kilograms. We're about 6,250 or so, and we'll go up from French Guiana. So we leave the Earth here, which is in this spiderweb gravitational system of the Earth-Sun. So the Earth is right here. The moon's orbit is this green circle, and the sun is way over there on the lower left side of your screen. We will go past the orbit of the moon. What did I say? The orbit of the moon is this circle. This green circle is something else. We go past the orbit of the moon, not quite drawn to scale. And in about 60 days, we make it to L2 over here. L2 is not a single point in the Earth-Sun system. It's a point that goes around with the Earth, but it has some fuzziness. Every 365 days, And it's a semi-stable, it's not actually a completely stable Lagrange point. You can't stay in it forever. If you don't do thrusting every couple of weeks, you will drift out of it and start orbiting the sun independently of the Earth. But if you follow the Earth around the sun, what you get is a semi-stable orbit here where you can describe what we call a Lissajous figure. And we make a vertical amplitude in that orbit that's about as big as the horizontal amplitude, and they're about 1 million kilometers each. So we go roughly 3 to 5 times further than the moon. And we are in very empty space. Low Earth orbit at 350 nautical miles contains tens of thousands of satellites and debris. In L2, which is 10 to the 18 cubic kilometers across, there's only a handful of satellites, and most of them have drifted out by now. So it's a very dark place. You can observe the sky more than 70% of the time. It's not like going around the Earth every 96 minutes where you can only observe half the time. So you have seen this already in the movie, so I'm not going to say much about it, except that all the components we make, we can only make and test in 1 gravity. And then we have to make sure it also works in 0 gravity. All the flight mirrors have been made, and they were polished and tested a long time ago. They are 1.35 meters across, about 4 feet across, and they're made out of beryllium. Beryllium is in the upper left corner of the periodic system, just like aluminum. It's above aluminum. It behaves the same, except it's very highly poisonous, unlike aluminum. And aluminum is very lightweight and not very stiff, as you know from the structure of an airplane. The airplane wings flap and so on. Beryllium is actually very sturdy. It's much more lighter weight than aluminum, but it's very, very stiff. And so between between 40 degrees Kelvin and room temperature, it doesn't change its size very much. So it's a very stable thermal system. Behind this mirror, all 18 of them, are 3 sets of redundant fingers. We call them hexapons that provide 7 degrees of freedom. There's a tip and a tilt and a translation in X and Y, and an up and down motion in the Z direction, and then a radius of curvature. So we can move this mirror with up to several millimeters in any direction we want, to an accuracy of 15 nanometers or better. So of the order of 10 to the minus 8 of a meter. And of course, you need to make this mirror to have exactly the right shape at 40 Kelvin in order for the light to focus. So all the hardware has been made. It was made a good number of years ago, actually, in the mid 2010s. Here's a primary mirror, gold coated. You guys, why we gold coat these mirrors and not put aluminum or silver on it, like with the Hubble Space Telescope? But why do we put gold on this mirror? It's not because the project has so much money. Anybody? Check the chat real quick. I'll tell you. You get extra credit if you know the answer. I can't seem to open the chat. Anyway, doesn't matter. If there's an answer, Tom, you'll let me know.
Yeah, let's see. I think somebody, oh yeah, there's a couple, yeah, there's a bunch of theirs in there. Let's see, IR reflectivity, thermal stability,
Yeah.
gold is more malleable.
Yes, the high IR reflectivity, you know, my wedding ring is gold. That's why it looks orange. Infrared light gets reflected at the 98% level by gold. By silver, it's much less, it's 91%. That's why silver looks bluish. And so you get much more light coming through. And if you had only one mirror, it didn't matter so much if you lost 10%. But we have 14 reflections from primary mirror to secondary mirror through the doghouse here into the instrument package that's behind the telescope here in the middle. And then inside the cameras and spectrographs, there's easily another 10 reflections after you exit the tertiary mirror. So you go from primary mirror to secondary mirror over here before it was gold coated, to tertiary mirror and fine steering mirror. And then you go into the instruments, which are packaged in this big box that is minivan size behind the telescope. And I'll show you more about that hardware in just a minute, but this has all been fabricated and assembled. So 100% of the mass has been built. Not all of it has been weighed in total yet. They could have missed a few screws and bolts. More about that later. They also reserve the right to add a few more weights here and there to make sure the center of gravity is in the right place before they launch it. So this is the family portrait of the entire telescope as it was built over the last 15 years. So in short, this is what was done. There's the primary mirror segments, of course, the secondary mirror to the left here. This baffle, or the doghouse as we call it, is where the light gets collected and reflects off the tertiary and the fine steering mirror into this module here, where the scientific instruments sit. There's 2 spectrographs and 2 imagers there, as we will see, and they all have redundant functions. So that's the package we have. So let's see, here in the middle, top, you can see the Sunshield as it has been deployed, with NASA standing right next to it. NASA has its ducks in a row here for the Sunshield, as you can see. This is the primary mirror support structure, the carbon fiber structure, which also has very low thermal coefficient of expansion before the mirrors were mounted. And in this device here in Goddard Space Flight Center, building 29, many of you who've seen Hubble before it was launched, or the Hubble instruments before they were launched. This was done in the same room, and it is upon this bed of structure that the mirrors were mounted. So this was done in the mid-2010s, after all the mirrors were made more than 10 years ago. There's a big robotic arm here that lowers all these mirrors in place to within micron precision before the hexapods are mounted and before you can start moving with tens of nanometers of precision. These 2 mirrors you see here were engineering models. They were backups. One of them wasn't gold coated in case somebody dropped a wrench on a mirror. That hasn't happened, but we had to be careful, make sure that over the many years that these things were exposed to the atmosphere, no damage was done to them. So this was a couple of years ago. I should have put the date there, 2016, when Rolf Jensen, Seth Cohen, and I were out in Goddard Space Flight Center during the mega snowstorm of January 2016. At that point, Building 29, which is one of the largest buildings NASA has, at least at Goddard, its roof is large enough to hold 2 Olympic swimming pools. And indeed, it had 2 Olympic swimming pools worth of water on top, known as snow. And so we had to make sure that nothing would leak onto the telescope surface. NASA was initially vehemently against it, but I insisted in 2005 that we should have some mirror covers. They didn't like that, but they provided mirror covers anyway. So here you see the fully assembled telescope mirrors with the covers on top. And so if you ask how the technicians put these mirror covers on and off, the answer is very carefully on 2 Olympic-sized diving boards where they're strapped down. So this was a very delicate process, and they did this carefully. And the mirrors are as clean as they can be. They're not completely clean. They have done another round of cleaning since then. They basically hose it down with carbon dioxide, I think, and try to mop up the pieces before they fall back onto the mirror. And of course, the mirror has been staring at the ceiling for many years while other things were being constructed. So this was a good thing to do. Here you see the full telescope in its glory after it was built. This was before the instrument package was put on. This is also in Building 29 of Goddard. You see the NASA meatball on the wall here, the logo in the back. And in the next picture, you can see how the telescope, who is mounted here on a merry-go-round, so you can rotate it every which way and tilt it every way you like. You can see the entire team here, at least the Goddard team in front of the mirror. The tall guy over here is John Mather, the project scientist that cracks the whip, make sure that everybody does their work. He's actually not the manager, he's the scientist. He's also a Nobel laureate. And you can see the NASA meatball that was visible here in the back, on the back of the wall, is visible in the mirror, and it is enlarged. So good, the mirror works, it's enlarging, right? So we have a working telescope. It's not in focus yet, but it does what it's supposed to do. It even spells the word NASA backwards, as you can see here. So great. We're on the path to making a working telescope. There's the telescope again on the mirror merry-go-round with the secondary mirror folded backwards and the two arms. There's a mechanism here, the bottom middle and one on the middle right, that can put this big V-shaped fork up and down. And so all these mechanisms have been tested, and there's backups for essentially all of them to make sure nothing gets stuck in flight. All of these mechanisms, or most of them, only have to work once. But we want to make sure that they work 100% the first time around. So then in that minivan-sized package on the back behind the mirror are 4 instruments. There is the U of A near-infrared camera that we're also closely involved in the sense that it does most of our science program. It works between 1 and 5 micron. Then the Europeans built a near-infrared spectrograph that also works between 1 and 5 microns, but it splits the light up as a function of wavelength. And they also built a mid-infrared imager and spectrograph called MIRI that works between 5 and 29 microns, shown here. And in the upper left, you can see the Canadian fine guide sensor that not only takes a picture of a star in both corners of your detector every time you lock onto something, so you can hold the telescope still against rotation and translation of the kind that was talked about earlier with the wonderful cameras you can mount on your own scope, but it can also back up as an imager and a camera. So there is more than 27 states involved in the US in building the telescope and working on the science program. It's closer to 40 states by now. And that was, of course, essential when the program got into political trouble over 10 years ago, plus about 16 European countries and Canada, of course, also shown here. So it's a big international project, and that's one of the reasons we're still alive today. These projects are hard to cancel, but also much is expected from you. So imagine you're taking a deep field like the Hubble deep field or ultra deep field or a cluster lensing field, and you want to measure the spectra, the redshift, and the chemical content of not just one galaxy in the field or 2, but 10 or 100. You like to have a device that looks like a little checkerboard with little mechanical shutters. We call them MEMS, microelectronic mechanical shutters that can open and close at will magnetically, driven by an electronic circuit. And you can then open up the shutters that are in front of where you expect the galaxies to be. So you first have to take an image so you know where the galaxies or the stars will be. And then you open up the appropriate shutters. And then every open shutter will produce a cigar worth of spectral light over here with almost 100 cigars in the image displaced from each other horizontally and vertically with a few overlapping cigars. So you can analyze the light of all these images as you have selected them here. You can make any pattern with this MEMS array. It has 62,000 of these micro shutters 4 times repeated. Like you could make the JWST logo here, which would not be terribly useful, but you could. And when you do that, you see that there's a couple of shutters that are failed closed, which is no big deal. They don't all work, so you need to wait to the next exposure. You move the array over a bit and take the next galaxy the next time around. It was covered, if it was covered by a failed shutter. Some of them are failed open, and they had to be painted over with epoxy so they don't cause any stray light. So it's not a perfect system, but it's a very efficient system. And the sky is very dark there, so you can make very dark images and spectra of stars. Here you see one of the 2 side panels of the mirrors fold into place, and you can see how tightly the mirrors fit together with only a few millimeters to spare. This is sort of the last portrait of the telescope before the instrument package was mounted on the back, which has been mounted here, and before it was tested and shipped to Houston, where it underwent complete electrical and system tests, and then to Northrop Grumman in Redondo Beach for the final assembly. Many of the things, as I said before, that need to work flawlessly, need to work both in 1 gravity and in 0 gravity. So the secondary mirror, which is here, these arms in the back and folds forward like that, sitting over here, will need to be tested not vertically when the motor will be overloaded and burn out because of gravity, but it has to be tested horizontally. I'll spare you the movie of this. It takes many hours or days, but you can imagine how that works. Here's the motor with the redundant one not even used, folding the secondary mirror into place. This is before the two side panels move forward. And while this happens, you can see many technicians run around, and there's cables, you know, going here and there. I say, well, they're cheating. They're moving this thing with cables. No, they're not. They're just offloading the gravity. So the secondary hangs there essentially weightlessly. And these three arms hang there weightlessly so that when the motor gets run, it doesn't overload and it does its job. And it did that several times. Then when you're done with that, you want to test this entire package. So telescope and instruments, all four instruments cabled up here in a giant tank. And that is done here in Houston. For the record, the telescope doesn't fit in the overhead compartment of your airplane. So you put it in this big container that takes not an 18-wheeler, but 36-wheeler truck and 2 freeway lanes to bring you from the airport to the building in Houston where the testing is done. And the only airplane in the world where this thing will fit into is a C-5. So that's how we move the James Webb Space Telescope. It will also go into this enclosure early next summer, and then it will be shipped off from Redondo Beach over the 405 freeway to San Pedro, put on a boat, go through the Panama Canal, past Venezuela, and get into French Guiana. There will be Marines on board to protect the thing. So it was here in Houston to go behind that giant 14-meter door that I think you can see open here from the inside. So that thing over there is the door. And this is the largest thermal vacuum chamber in the world. It is 5 stories high. And in the Apollo era, the Apollo 11 moonlanders and capsules were tested here. So not the entire Saturn V, of course, but the upper stage was tested inside this chamber. The chamber is still around and it was refurbished for the telescope. So you put the telescope in the chamber, and then at the top of the chamber, not shown here, is a complicated testing tower. What you do is you remove the technicians here, then you close the door, you pump the thing vacuum in that order, and then you cool it to 40 kelvins. And then you have, as close as it gets, except for the gravity, you have an environment that looks like space, and you can test how the telescope works in the dark. Then you have to make sure that there is enough leeway in those 6 fingers, 18 times repeated underneath each telescope, so you can move each mirror panel exactly with 10 or 15 nanometer precision and get in-focus images. And these in-focus images are slightly different in 1 gravity than there are in 0 gravity, but there is enough leverage in this system that you could make it work for both gravitational environments. I got to point out here, and I say this with a little tongue in cheek, some of you are old enough to remember this, that the Hubble Space Telescope mirror that you saw earlier didn't work so well the first 3 years. It was the most precise mirror ever made at ultraviolet optical wavelengths, exactly to the wrong shape by mistake, right? There was a spherical aberration in this mirror. Now listen carefully, this James Webb Space Telescope is the most precise infrared mirror ever made at room temperature to the wrong shape. So when you move it to 40 kelvins, the beryllium will take exactly the right shape. So to first order, while the telescope is designed to the wrong shape at room temperature, it's by design such that when you bring it to 40 Kelvin, it has exactly the right shape. And that was verified in this chamber. So we know with certainty that this telescope doesn't have spherical aberration. It may have other problems, but it doesn't have that. So then there is the tennis court size Sunshield that's being enrolled here at Northrop Grumman in Redondo Beach. This is before the telescope is mounted on it. These 5 layers of Kapton here are currently folded in, and there's movies on this, but then they're folded out as you saw in the movie, and this is done with many technicians there and with lots of cranes and installations that also offload the gravity from that sunshield a good bit. Because if you do it in one gravity, it starts sagging a bit. And when the sunshield is completely folded up in the aft and forward pallet structure here, it looks like this. This is before the telescope gets mounted. That was in August last year, so only a year ago. Then since then, the telescope itself was moved from Houston, again via C5, to Los Angeles and brought to Redondo Beach with the same truck and mounted on top of the telescope. So this is sort of the last picture of the telescope. You can see how large it is with the two side panels folded backwards before it's mounted into the Sunshield and spacecraft.
Hey,
And that's yeah, go ahead.
Might not be a bad time to just take a couple of the questions that are
Sure.
that have queued up.
Absolutely.
One of them was asking what sort of redundancy do you have for all the series of movements when it's unfolding? Is there some, what if it gets stuck, or they're just wondering,
So for the secondary mirror, there's a motor here and a motor here. They tested both, but they only need one. For the two side panels, which you really like to have, but strictly don't need, you still have a functional telescope if you only had this. You also have two mirrors that move it forward so two motors that move it forward in zero gravity. The Sunshield is a bigger deal because that needs to be, it's like the giant sail of a sailboat, but 5 of them, of this Kapton, this highly reflective material that needs to be held down during launch, as you can see here. So there is 103 pins. They're about the size of my finger. Let's see where I have a pen here at some point. And it's like a clicking ballpoint. You click it once and it comes in and out. And these things have redundant mechanisms. All 103 of them need to come down to release the Sunshield from its mounting on the pallet structure where it needs to be mounted during launch. Because during launch, where you go from atmospheric pressure to zero pressure in the course of about 8 minutes, like in a sailboat, this Sunshield will really start billowing because of the air wanting to vent out. So you need to keep it down during launch. And so each one of these pins that holds it down will get retracted. And there is a primary mechanism and a backup mechanism. And when they decide this, they tested each one of them 26,000 times, and they tried not to have any failures. When they mounted the real things about a year ago, of course, there was one that didn't retract on the primary, but it retracted on the backup. And so they have looked into that and replaced that also by another one that didn't have this problem. So the backup mechanism in this case with these retracting pins fires together with the primary mechanism. So all 103 of them need to come out right away. These telescopic mechanism, let's see, where is that now? I really need to, I guess, use this to go back and forth. Where you saw it was visible in the, I guess it's best seen in this image here. Sorry about that. I'm trying to find the right image. Where the arm over here on this side and on the other side comes out, that has a pretty strong motor and that carries the Sunshield with it. There too, there are redundant motors. But there is some risk there, and they try to mitigate all this risk by testing it out on the ground. And anytime anything gets stuck, they figure out why it is and do a new mechanism and put a new mechanism in.
And there's another question of how much time will it take between launch and first light? I guess that means fully deployed mirrors and ready for calibration.
They won't guarantee anything for 6 months, but I think they'll have something pretty crude in 2 months. They will have the thing completely unfurled, probably in a month. And then they need some focusing and testing, which is, I have some backup charts on that. That's a pretty big ordeal, actually, because you need to make sure that all 18 mirrors with all 6 hexapods behind it are completely in focus to within a few tens of nanometers. Okay. And that takes a number of weeks. They count 2 months for that.
All right. And two more short ones. Will JWST be visible through a backyard telescope?
I knew the answer on that once. I think the answer is no, but a medium-sized telescope will allow you to see it. It's not that small,
Mm-hmm.
and it's not that faint, but it's also lower surface brightness because it's so large. And you have to see it at just the right angle, at just the right location. And you have to know where you look. I mean, many of you can go to Google Sky and do satellite hunting. You find the space station overhead or the Hubble Space Telescope right at sunset or sunrise, and that's not so hard to do. But all these things go around the Earth at very irregular orbits. Here's something that dances around in three-dimensional space with an amplitude of 1,000,000 kilometers in a period of a couple of weeks. So it's much harder to find.
Okay.
And it won't be quite an L2.
And one other quick one is Hubble's been visited several times for repairs over the years.
Yeah.
Why isn't JWS, or is it possible for JWST to get visited?
Well, that's a good question. I asked that question to the project in 2005, and I was berated by saying, well, we don't need it because we have so much redundancy. And we have so many other missions we can talk about where we think we don't need this for JWST. That was the kind of answer I got. And then we had a new NASA administrator a couple of years after that. And he came after O'Keefe. I forgot the name of the new administrator. And he asked the same question, how come you guys don't service James Webb? And John Grunsfeld asked the same question too. The astronaut wanted to actually go to L2 with the next generation launch vehicles and fix it. The answer is there is so much redundancy in the telescope that they think they don't need it. And it would have been too costly and another delay. So this is a completely different paradigm than with Hubble. Hubble would have never lasted 30 years if it had not been for the astronauts servicing every 4 or 5 years. And that is not true for James Webb.
Okay. Yeah, I'll let you continue on this time. The other
Okay.
questions are a little more lengthy.
Yeah.
Go ahead.
All right, well, we'll have more questions at the end. I'll be happy to stay as long as needed. So here's the telescope being mounted onto the Sunshield with a big crane on the yellow track in the ceiling there. And there we go from various angles. So now it is an observatory. And here it is. It looks like the strong man with the mirrors folded backwards. And you can see along these two pylons over here is where the Sunshield with cables, this was actually the hardest part, the Sunshield with cables gets pulled up layer by layer. That got stuck once, and the reason it got stuck, there was a small millimeter, a couple of millimeter size ball of epoxy that had come off of something else and had a cable stuck in one of the mechanisms over here. And they got to the bottom of that and fixed that and checked that they had no other epoxy anywhere else where that could have happened. The cables, of course, are pretty tight when everything is moved up with the 5 layers separated, but they also have some slack in them. So that is something they have exercised a good number of times to make sure they can do that flawlessly. So here is as of earlier this spring, the solar panels. This is folded up and this is being deployed. This is also done in one gravity hanging off the ceiling, of course. But the motor, so this is now done with the motor. There's technicians to decide, but the motor that does it only provides the horizontal motion. So that's essentially free of gravity. And there's the Sunshield, the solar array fully deployed. And here it is mounted at telescope. It's actually, it's pretty sizable, but also pretty lightweight. And that also has a redundant mechanism in it. You need that because you need a couple of kilowatts of power because it's, a pretty sizable observatory and it needs a good bit of cooling inside. Then the last thing they had to test is that 1 meter tower that telescopes out here with the telescope being pushed up by it so that it separates from the Sunshield so that the other parts of the telescope can deploy. And this is being done here by offloading with a crane from the ceiling. So they test this while they give it just the amount of counterforce that the motor needs to show that it can do this in zero gravity, and there it moves up until it's done. So that's what happens also after launch. And then here finally you can see how the before it is going into the final test for shaking, how these two panels with Sunshield fold backwards and forward. So here is, hang on, I guess you can see that here, where that panel with its own motor, but gravity offloaded, comes all the way up. It's only the one to the right that's shown here, but the one to the left does the same thing. And it's very tricky business because you have to get the forces just exactly right. And they've done that. And then finally, this happened, a month and a half ago. They put the entire thing in a tent to protect it from bird droppings and so on. This is close to the beach after all, so there's a lot of seagulls here. And they move it from one building at night to the other building where they do the acoustic tests. This is apparently one of the riskiest parts, at least on the ground, of the entire operation. Because if they get a major earthquake here, they don't have a crane to hold it still. So, they hope for not an earthquake during the hour that they're moving it. Once it gets into the acoustic chamber, it is pretty well bolted down, and then they test everything for launch vibrations plus another factor of 2 or 3. I see there's a few other questions in the Q&A. I'm ready now to get to the other science part. So if you want to break for a few more technical questions, I'd be happy to take them, Tom. We can figure out where the questions are.
Let's see.
Ah, here.
Yeah, I do. So yeah, delay of launch, that could be a whole lecture all by itself.
Yeah, I have spare charts on that. So if you hang around until after the science part, I'll be happy to talk about that. So the major delay from the original launch date has been that they had no good way, or no way really at all, to estimate what this would cost. When you make a mission like this for other purposes, you can only imagine what those purposes are. It may come out of budgets that are much larger than NASA budgets, and budget overruns may not be as relevant. In this case, we started out with a little less than $1 billion budget. And after 4 or 5 years, that had more than doubled. And that was actually none of their own fault. That came through a very tricky business. I don't know how much detail you want to hear, Tom. Should I keep this for the end?
Yeah, I think you still have a lot of science to go through.
There was politics involved, and then an inability to estimate what it would cost to do this correctly. And then, they realized they couldn't cut any corners at no stage in the mission, certainly not in the end. So they want to get everything right and cost what it costs.
Then they wanted, how do you stabilize the mirrors so they don't get destroyed in the rocket launch?
Oh, well, these beryllium mirrors will have been shaken a lot harder than what Ariane gives you. Ariane is a pretty smooth ride, like the space shuttle. It's still pretty rocky, but it's no worse than going up and down on a pogo stick.
So by design, huh?
By design. So yeah, the beryllium can handle that. There is some concerns about the launch shaking. They keep the launch shaking to the minimum they can, and the French have been very good at this, the Ariane rocket. These micro shutters, the 62,000 4 times repeated in the NIRSPEC spectrograph, they come loose easily, and they are close to the limit of what the launch provides. They have been tested slightly over the limit, and some of them have come loose, which is why you saw the empty holes in that array. Let's see, you should go back here.
Yeah, I think we're ready for the science part.
Yeah, all right. So here's our wide field camera 3. This is the one that we're involved with Hubble, that was remade from the original wide field camera 1. So it was a relatively easy job to do because we knew it already fit in the telescope. This part here, this curved shield, is the titanium shield that makes the outer part of Hubble. And so this camera was launched in 1990 as wide field camera 1. The Hubble Space Telescope, of course, it didn't work because the mirror had the flaw, and was brought back by the astronauts that installed the wide field camera 2 in 1993. And then we had 20 years to remake it. So in 2009, or 16 years. We replaced it by the good old wide field camera 1, but with completely new detectors and filters and everything else, and that's wide field camera 3. So there you go. And so let's see what this thing can do. First of all, you can actually see pictures of the wide field camera 2 in the Smithsonian. I have a backup chart of it somewhere. And of course, the wide field camera 2 was in space for 16 years, and so will be James Webb. So this titanium sunshield was pretty significantly pockmarked by micrometeorites. It's about 2 square meters, maybe a couple of hundred micrometeorites. None of them was big enough to cause a hole or any permanent damage, but the meteorites were maybe 5 or 10 microns across, dust particles basically that come in at 30 or 40 kilometers a second. And they create little pockmarks in the titanium. And they will do the same to the JWST mirrors over 10 years and also create holes in the sunshield. So there will be holes in the sunshield. But like we do every year with Hubble, when we go through the Perseids, right, the meteor shower that's there on August 10, 11, the tube of the telescope gets pointed, if this is the telescope, if the cometary trail that forms these micrometeorites that goes in elliptical orbit around the sun is elongated like this. You try to align the telescope such that it has a minimal cross section against those meteorites impacting it. And you do the same for the JWST sunshield as much as you can. When this swarm of meteorites come by, you make sure you're not aligned like this, but under a significant angle as much as you can, so you get a minimum number of holes through the sunshield. So with that wide field camera 3, we have made these kinds of images, and a good number of folks in my group have been involved with this, such as Seth Cohen, Wolf Jensen, a number of other folks. We did this in 10 filters with the wide field 3 and the advanced camera for surveys, the ACS, reaching 26.5, 27 magnitude over about 40 square arc minutes. And the resolution is typically somewhere around 10th of an arc second. And this image ranges all the way from 0.2 to 1.7 microns. Here's the filters listed, so from the UV all the way into the near infrared. And then the James Webb Space Telescope will add to this imaging that is of the same or better resolution, about 4 or 5 magnitudes fainter, 31.5 magnitude, which for radio astronomers like Tom and me, that's about 1 nanojensky. And for those of you who don't think in these terms of magnitudes or genskys, it's equivalent to 1 firefly, 1 FF at the distance of the moon, with the moon not there, of course. So 31.5 magnitude, 1 nanogensky, or 1 firefly. So the telescope can see the equivalent of a firefly at 1 micron at the distance of the moon, if the moon weren't there. We, of course, avoid the moon like the past. We don't point. So there's 3 things we can point at, 4 things, 5 things really, with James Webb, right? You can't point at the sun because you'll burn everything. You can't point at the Earth, that's not a whole lot better, or the moon. You can't point at Venus and Mercury either, because they're all too close to the sun. So anything we're pointing in this direction for our object of interest, the sun and the moon and the Earth, will be in this direction over here. And they're all behind the sunshield, except the moon occasionally comes slightly over the sunshield and will cause some extra stray light. But we'll get images like this, but I'll show you in a minute what they will look like. They will be much deeper and much redder. Now, these are nearby galaxies, nearby, quote unquote, about 1 billion light years away, a redshift of a few tenths. And they got a lot of active star formation in the center, which is why they're so bluish purple. But they got a lot of older stars in the outskirts, which is why they're so orangey red. And then there's more spiral galaxies like our own over here. And then there's all these distant galaxies, which are a redshift of 1 or beyond, where the universe is half its current age. And the galaxies also start looking much different. And then there are some very red faint objects. I'll show you some others later, but one like these or like these, which are very distant, where the universe was very small and very young. We call them high redshift galaxies. So that's just a flavor of what to expect. And by the way, there is in this image maybe 1 galactic star, and I can never find it when I look for it. If somebody sees it before I do, you can tell me about it. If you make a much bigger image, you'll see more galactic stars. So in other words, if you imagine you're driving on a highway at night and you see the distant lights of a city or a suburb and along the highway in the distance, each house being a galaxy, that's what you're seeing here. And the drops on the windshield, or the dead flies on the windshield, are the stars in our own galaxy. There are so few stars in our own galaxy compared to the distant galaxies out there that you'll be hard pressed to find them here. I'll show you some others in a minute. I can't resist the temptation to do a little excursion on black holes, because I know everybody worries about it. And so just for the record, for those of you that don't think about this every day of your life, which you don't have to, there is three kinds of waves, right? There is waves in solids, like earthquakes. That's a wave in the concrete of a road when the earth gets cracked due to lateral shift of continental plates or something like that. There is waves in water, which we call surf. And then there is waves in air, which we call sound. And then we have electromagnetic waves, which run all the way from long wavelength radio to very short wavelength gamma ray, with everything in between, such as microwave, infrared, optical, ultraviolet, X-rays, gamma rays. And typically the objects that cause each of these waves are of the order of the same size. So gamma rays are caused by atomic nuclei, and X-rays are caused by atoms. Ultraviolet are caused by electrons circling around atoms, and visible infrared is caused by molecules or larger things such as needles and butterflies. And then microwaves are caused by peoples and rockets and black holes. But in addition to all these waves, so solid, liquid, and air waves, and electromagnetic waves, you also have waves in space-time, and those are the gravitational waves. And those have been first observed in 2015 with the Nobel Prize shortly thereafter for Kip Thorne, the one who did the movie Interstellar. And these gravitational waves typically happen when two compact objects, mostly by black holes, possibly also neutron stars and black holes, when they merge, they basically distort the space-time between them and surrounding them. And that gives you a detection of gravitational waves that has been observed. That was observed here with these two L-shaped detectors, lasers that are 4 kilometers long, that try to find the ripple in space-time that's caused by these gravitational waves. I'll spare you all the details except to say that the gravitational wave detector in Hanford, Washington, and in Louisiana, they were 2,000 miles apart, and they saw it with a slight time difference. And they saw exactly the same pattern, but a mirror image of it. And the top is the observation. The middle set of panels is what they observed, what they modeled for a black hole merger of somewhere around 30 solar masses, to be precise, 29 and 30 solar mass black holes. The astute student will have calculated that it's 65 solar masses of black hole merging here. That's not actually what they observed. They observed the outcome was 62 solar masses. So where did the other 3 solar mass go? Well, exactly, it became energy. So a full 3 solar masses was evaporated in a fraction of a second by using Einstein's famous equation E equals mc squared. And so we know we have these baby black holes, and they are the aftermath of the stars we see with the Wide Field Camera 3 and also soon with the James Webb Space Telescope that form everywhere. These young hot stars, they're between 10 and 30 solar masses typically, and they will leave a modest black hole behind between 3 and 10 solar masses. And the LIGO black holes you just saw were, sort of 30 to 36 solar masses, and they came from maybe 50 or 80 solar mass stars. Now, I call these stars jokingly the cosmic fraternity members because they live fast and they die young. They only live 3 million years because they're so massive. And it is in the aftermath of these stars, and these, by the way, are not even in our own galaxy. They're in the companion galaxy, the Magellanic Cloud, the Large Magellanic Cloud. And here at the end of this dust finger to the left here, you can see a finger that looks just like that. It's a pillar of creation, just like the Eagle Nebula, but now it's in another galaxy. It's in the Magellanic Cloud. You can see at the end of that finger, not in the optical image here, It's an enormous gas cloud. This Christmas tree looking thing that's brown is an enormous gas cloud. But out of this gas, shaped by the ultraviolet radiation of these stars, are new stars forming. And over here is a star forming that is the mass of the sun. So these baby black holes, they're like my child when it was young. It was not very efficient in eating. Most of the eating actually did not result in the black hole growing. And that is true for babies. That is also true for baby black holes. We think some of these baby black holes, the 30 solar mass black holes, may be left over from the very first stars, the first 500 million years, which were between 50 and 100 solar masses, we think. And they have not grown much since. So that's why I call them the baby black holes. They're probably too massive to be left over from ordinary supernova explosions that you see occasionally in our own galaxy or the Magellanic Cloud. So why are they only seen to be merging now by LIGO 12.5 billion years ago? Well, the answer is they probably were not very fast and efficient eaters, but slow and messy. So that's category black hole number 1, the baby black holes. Then there's other black holes, the so-called supermassive ones, and these are the ones we're after with Hubble and James Webb. And they sit in the centers of galaxies. And in the center of every massive galaxy, especially elliptical galaxies that look like this big pile of orange stars, there's about 1 trillion stars in this galaxy. And this is the massive galaxy Messier 87 in the center of the Virgo cluster, only 45 million light years away from us. And it has this relativistic jet coming out of the center here, which comes from the accretion disk of a supermassive black hole. It is not unlike shining the laser pointer at somebody in the audience. Don't do this in real life. But out of the center of this galaxy is coming an extremely bright beam of light in gamma rays, in radio, in X-rays, in the ultraviolet, in the optical, microwaves. And it points not quite in our direction, it points in a different direction this way. Had it pointed straight into our face, we would have called it a quasar. And in either case, about 0.5% of the baryonic mass in the universe sits in these supermassive black holes. And so this is category number 2. And they populate the center of every galaxy. More recently, and this is a graph I couldn't resist throwing in, it was discovered in April last year that this very black hole in the center of M87, when properly imaged with infrared, or rather microwave telescopes, all across the Earth, all the way from Hawaii to the North Pole to the South Pole and all across the Americas and Spain, produced a smiley face image of the accretion disk around the black hole. The smiley face actually changed slightly over time. And the best explanation is that the accretion disk around the black hole, which of course constantly feeds material into the black hole, is imaged into a ring, like an almost complete Einstein ring around the black hole. So the black hole is in the location of the shadow in the middle. And that disk is a disk that's probably seen almost tilted edge on, but because of the gravitational lensing, it gets shaped in an almost perfect arc. And the size of the arc, I make my students in the 322 class do this for homework, is about 6.5 billion solar masses. Now, those are real black holes. Those are rapidly eating black holes, and they sit in the center of every galaxy, like our companion galaxy, not Andromeda, although Andromeda also has a sizable black hole, but Centaurus A has about 10 to the 8 solar masses sitting in the middle, and lo and behold, a jet of relativistic X-rays and radio waves generated by electrons that come from the accretion disk surrounding the black hole in this galaxy, which is highly enlarged here. You can't see it directly because it's hidden by all the stars and the dust that create the new blue stars that you see surrounding this galaxy in the outskirts. But the black hole is in the center, all right, and it is all the same object, and we think it's about 10 to the 8 solar masses. Now here is one that we saw with our own Hubble Space Telescope. Some of our own folks have worked on this at a redshift 6.4, when the universe was 7.4 times smaller than today and about 900 million years old, so less than 1 billion years old. This contains a massive black hole, also a few billion solar masses. and it has an accretion disk that's about the size, slightly larger than Pluto's orbit. And from that accretion disk, 40 AU, if you think in terms of the solar system, comes a luminosity of 10 to the 14 solar luminosities. Now, may I remind you, last time we went to Pluto with New Horizons, we looked back at the sun. There was precisely one star within 40 AU that would have been the sun. Here, if you sit at Pluto's distance from the center of this supermassive black hole, you see 10 to the 14 solar luminosities. Now, that's a good place to get a suntan. It will kill you in a picosecond. And so these are one of the most luminous objects in the entire universe. A, they're the most distant, and B, you can see them not quite with the naked eye, but a small telescope will do. So this is a feeding monster black hole, 3 billion solar masses, 900 million years after the Big Bang. So that's not like a baby eating spaghetti and spilling most of it on the floor. That's more eating like my cat. My cat is overweight. It always eats, and it never stops eating. So that's the second generation of black holes we have. They feed enormously rapidly in the first billion years. They were eating catastrophically and secretly until they run out of food, like my cat. And what the James Webb Space Telescope will do now is see these very first quasars, we call them quasars for quasi-stellar radio sources, which surround these first billion solar mass black holes, if we can find them, and I think we can. The great mystery is that, you know, this black hole universe comes in two kinds, the big fat cat kind and the baby kind. There seems to be nothing in between. So it's either a billion solar masses or 30 solar masses. And what gives, you know, how do we go from such small to such large black holes? Well, we think they ate very rapidly, and we try to figure out how they did that. By the way, our own galaxy, which is shown here, this is a real image as Rick Alling or the other folks would take for you with their beautiful cameras of the Milky Way, with some real mountains in the foreground. And this companion galaxy is our own Andromeda galaxy, which Hubble, the astronomer, showed is not redshifted from us, but it's blue shifted. So it's actually moving towards us at about a couple of 100 kilometers a second. And then 100 years later, almost 100 years later, the Hubble Space Telescope showed that not only Andromeda is moving towards us, but it's also having no lateral motion. So in 5 billion years, it will not just not fly by, but it will pancake right on top of us. So this is today, upper right, 1 billion years, 2 billion years, 3 billion, 4, and 5 billion years from now. These two galaxies will merge. They will form a giant elliptical, and their two central black holes, 10 to the 6, 10 to the 7 solar masses right now, will merge into a super big black hole and form a small quasar for one. There is no need to worry because this will not happen until 4 or 5 billion years from today, so no need to sell your real estate just as yet. And the sun will burn out before that time anyway. But that's our future. So now if we imagine that this whole cosmic web of stars and gas that forms these first stars that's out there at in the first few 100 million years, forms these giant supernova explosions and all these little star clusters that we just saw with the Hubble Space Telescope. We were going to try to find all these little star-forming clumps in this cosmic web with these occasional explosions and the occasional quasar, and try to figure out how this cosmic web came all about. And for this, to be specific, we use a filter set that's a little different from what we have in Hubble. Hubble has filters that's shown here, all the way from the UV to about here to the F150 filter. This is in units of 1 micron, so 115 means 1.15 microns in wavelength. And here you can see at the observed wavelengths what the spectrum of a blue galaxy or a blue star would look like as it shifts through these filters. We have 8 of them, and at a redshift of 6, this blue spectrum will look like this purple curve, redshift 8 like the blue curve, and so on, all the way to redshift 15 and 18, where the first 3 or 4 filters show no light at all, and the reddest 3 or 4 filters show a detection. And so since there's this rapid drop here at the basic wavelength of the hydrogen atom, 1216 angstroms, that is the light needed to kick the electron up from the first Bohr orbit to the second orbit, all the light below that wavelength to the left here is so energetic that it gets eaten away by the hydrogen and makes this transition. But all the light at longer wavelengths can come through, and so you can see the stars and galaxies that form that light. And so by picking objects that were not detected in 3 or 4 filters, but seen in the redder filters, we can find the highest redshift galaxies. We tried to do that here with the 600-hour or the 892 orbit Hubble Ultra Deep Field. You've all seen images like this. We showed them off at the School of Earth and Space Exploration Day in October. And this looks similar to the image I just showed you, but now it's much deeper. This now reaches the level of 1 firefly at the distance of the moon, or about 31st magnitude in the red. And some of these very red, brighter galaxies are ellipticals in the foreground. This galaxy here at 9 o'clock would be a spiral like our own, but probably 5 or 6 billion light years away. And somewhere over here are some of these very distant galaxies. They look very red because the universe was so small and so young back then, so it has expanded a lot since then and redshifted. And you can also see the, the drop on the windshield effect here. There's one galactic star here that is this asterisk looking thing. There's another one somewhere else over here, and there's a third one that's actually a quasar. I don't see it right now. But the number of stars in our galaxy in this image is extremely small indeed. Now, if we render this the way it should look for the James Webb Space Telescope, I actually use the same data. I just changed the filters. It will look like this. So it will all look much redder and much denser, but the blue colors are largely gone away. And I've now also penciled in with green circles where the objects are at redshift 7 or 8, where the universe is about 750,000 years old. And you can see, if you enlarge it, that there is some objects in each of these circles, and those were the ones that are seen in all but the 3 reddest filters. And then there are some objects at redshift of 9, where the universe is about 600 million years old. In the orange circles, I'll show you in a minute that they're really there. And then there's one object here, redshift 11, where the universe is about 400 million years old. And there's one object there that is barely visible. That's only seen in the reddest out of 10 filters. All the other filters have dropped dead. There's just no light there. And so if you pack all the light of all these 13 filters here into now what is a false color image, you can convince yourself that inside every circle, there is a real object. You have to enlarge it to see it. But there is in fact a redshift 11 candidate dropout here inside that red circle. You can see that the number of these objects is few and far between. We're now pushing back so far into the early history of the universe that there's very few galaxies out there. And we're trying to look for other methods to see these galaxies, like gravitational lensing. We take a foreground galaxy cluster. This would now be the downtown Phoenix or downtown Los Angeles of galaxies, where every house is a galaxy, and there's many hundreds, in some cases thousands of galaxies in these clusters. The total mass is of the order of 10 to the 15 solar masses. And with so much mass in such a small clump that's only a few million light years across, you can make gravitational arcs like we saw before in the lensed ring of that accretion disk around M87's black hole. And some of these galaxies, like these nice light blue ones, are repeated 4 times. So this blue object, and these two here are all images of the same object that are behind the center of this cluster, and they get lensed around the gravitational mass. The same true for these very red distant galaxies at the edge here, and this disrupted spiral galaxy here, there, and there. It's all the same image of the same spiral galaxy. Now this spiral galaxy is relatively close, maybe twice as far away as the cluster. But some of these other objects are very far away, probably redshift 7 or 8. And they're very stretched because of the gravitational bending of this cluster light. Not only are they stretched, they're also highly magnified. And that makes it a couple of magnitudes easier to see by as much as factors of 10 or 30. So we think by observing through these very dense clusters, we can look for these rare background galaxies, these very red objects that are seen at the dawn of time, an epoch we call cosmic dawn. I need to wrap this up. So you can see that these images get very densely packed. We will have to contend with two effects here. The so-called, you cannot see the forest for the tree effects. There's a lot of trees in the foreground, the galaxies in the foreground, and there's a much larger number of galaxies in the background that we also can want to see, especially the most distant ones, but some of the objects in the foreground block the background. And then it's also like the house of mirrors effect. Some of these galaxies are not seen once, but they're seen 3 or 4 times because the gravitational lenses are like a house of mirrors. And we need to disentangle all these images to precisely estimate the distances and the masses and the characteristics of all these galaxies. So I'll put my, let me, for the sake of time, skip this part and leave it for the spare charge, Tom, about the future telescopes. This shows you their true size. And that's the size of JWST in the Yankee ballpark. And I'll get you my conclusions here, and then I'll be happy to stay as long as it takes to answer more questions. So Hubble has set the stage to measure galaxy assembly in supermassive black hole growth in the last 13 billion years. And JW is now past the point where everything has been designed and made and replanned, and 100% of the hardware is built. We're now in the final integration and testing and see if there's any major surprises before we launch, because we can't launch a telescope without knowing that everything works well. So we're all set up to measure the first stars and star clusters in the first 200 million years, and how galaxies formed and ionized the universe after the first billion years. And then last but not least, point 4, we really want to train the next generation researchers. So I welcome any young folks and students in the audience who want to work on this kind of data and help us define the next frontier, which would be the dark ages at redshifts bigger than 17 or 20. So I'll leave it at that, and I'll open up for more questions if I can find the chat, and be happy to answer.
They're in the Q&A, Roger.
For some reason that doesn't come up here.
You're not seeing that? I can read it to you.
Yeah, hang on. Maybe I need to stop sharing for a second. Here we go. Yeah. And then let's see. So these are infrared detectors. These are Mercator detectors in the near infrared, and a similar technology. So they're silicon based, but they have other dopings in them, like mercury, cadmium, and telluride is the, and there's also something else that includes indium and antimonide. Yeah, the baby black holes do come from supernovae, but not ordinary supernovae. They're a little bit too massive for ordinary supernovae, so they probably come from the first or second generation of stars that is more massive. Okay, let's see what other questions that we have. Will JWST be useful in observing objects within our own galaxy or solar system? Absolutely. Jupiter, Mars, Saturn, Uranus, Neptune, Pluto, they're all fair game. You're just out of luck if you want to point at Venus, because that's too close to the sun. But that's it. And infrared signaling to dark stars. Yeah, let's for instance start with galactic stars, also answering the previous question. Any brown dwarfs, which are basically failed stars not much bigger than Jupiter, maybe 10 times the mass or 80 times the mass of Jupiter, that are not dense enough, massive enough to start nuclear fusion. So they're technically not stars, and we call them brown dwarfs. Those we can see. Purely dark stars that consist of dark matter, that is not so clear. There's various theories on that. But it's not clear what the observational signature of those is. So if they shine in the infrared, the answer is you could probably see them, but they have to be brighter than a firefly at the distance of the moon.
There's one way at the top, Roger. Will the JWST infrared images be complemented by other wavelength images?
Yeah, we're doing that right now with Hubble as if there is no tomorrow, because Hubble can do the ultraviolet and the blue optical that James Webb cannot do. So we're trying to image many objects in deep fields in the ultraviolet, blue, and visual wavelengths with Hubble before we no longer have Hubble and before JWST gets launched. So absolutely, yes. And of course, ground-based telescopes, like these 30 meters, I showed you some pictures here. This is the 30-meter or 25-meter Giant Magellan Telescope. That will be very nicely complementary to James Webb, because when we no longer have Hubble in a few years, then the Giant Magellan can take over some of Hubble's functions. It won't work in the ultraviolet, but it works great in the blue visual optical, and so complements Hubble. There is no liquid cryogenic. That's an excellent question, Sasha, but there is cryocoolers. So there is liquid sloshing around that gets cooled thermoelectrically, but there is no propellants or cryogenic, like a brick of solid hydrogen that gets evaporated and cooled the detectors. It's all done by passive cooling.
Do you know what temperature it tries to keep it at?
Well, most of the cameras are at -40, but the MIRI, the mid-infrared camera, where you have the most background from our own solar system and the telescope, that you need to cool the detector at least to 6 Kelvin. So they try to get that down to 6 Kelvin. They have shown that that works, but that's a big deal.
So 6 Kelvin without cryogenics, or?
There is a cryo cooler, so it's a cryo pump
okay.
that moves helium around and cools it when it comes out and then pumps it back in. But there is no consumable cryogenic, so there is no brick of solid, dry ice or solid hydrogen that gets evaporated over time. That was the case for previous infrared telescopes, such as the near-infrared NICMOS camera for Hubble that had a finite lifetime cryogen, as well as the Spitzer Space Telescope. What other materials were considered before selecting beryllium? Well, they looked at various classes, but they were too heavy and they had too much coefficient of thermal expansion, so they quickly settled on beryllium. And aluminum is not good enough because it's lightweight, all right, but it expands and contracts too much and it's too flexible. Best part of working at NASA, there's new surprises every day, I'd say. There's never a boring day. It gets stressful by times, and sometimes you have to wait 20 years for your mission to fly. But technology is out of this world, literally. And we observe things that nobody else has seen. So I think it's great. So the spectrometer that we use inside the near-infrared spectrograph is grating based, and the maximum resolution is 2700. So that means that you can roughly observe things with a precision better than in velocity, roughly 0.03% of the speed of light, which is pretty good. It is not as good as the large spectrographs you can put on these ground-based telescopes, but there, you can make much bigger boxes and use much higher resolution. But we have much darker skies than the ground has, so we can do much fainter objects. So the James Webb over here and the ground-based telescopes are really complementary. So ground-based is mostly optical, high-resolution spectroscopy, but with bright foregrounds. James Webb is mostly infrared, very, very dark backgrounds, but lower resolution spectroscopy. Absolutely, the dark matter in these images will, and as well as the dark energy also in the universe, will get carefully imaged or mapped with Webb, especially through these gravitational lensing clusters where we get very accurate dark matter maps. Okay, now let's see what else we have. How will data be relayed back to, no, it's the high gain antenna that works in the Ka band, yeah, 28 gigahertz. Maybe slightly higher, 32 gigahertz, but in that range. Yeah, a few years ago, Matt K, we had a question as to whether the propellant tanks could be completely filled. If we had been at our maximum weight of 6,500 kilograms, we would have to leave with half a tank of gas or 3/4 of a tank of gas. Since we're 200 kilograms underweight, we can carry a full tank of propellant, which means we have a maximum of 14 years lifetime. If nothing else breaks, we can operate till 2035. Now, something else could fail before that time or partially fail, but we have lots of propellant. I need to make this thing a bit bigger so I can see all the questions. They scroll off too quickly. What has been discovered since JWST? And did that change the mission? Well, Hubble has made many discoveries in the red and in the ultraviolet, but hasn't done much in the near infrared because it doesn't look much past 1.5 microns. And that's where the sky is the darkest, where you look deepest into the cosmological volumes. So much more objects past redshift 8 and 9 have not been discovered with Hubble, since it's simply running out of steam. So that's something you can only do with James Webb. The NASA Space Grant and interns, Simone, have helped a lot by doing, for the Webb program, as well as for the Hubble program, various data processing tasks. You're involved in one of these projects yourself with SkyServe and Hubble. But many of the data flows are so large, we're talking about many tens or even hundreds of terabytes, that we need all the help we can get to process the data, and that's where the interns come in. For the exoplanet field, I'm glad you're asking. Forgive me, some of the fields I won't show or I won't talk about this one, but we have some exoplanet charts since you asked. I also have some managerial charts. So in these blue star clusters, where bright new stars are forming, you can occasionally observe, you can even see it here, there are these pillars of creation. This is not the Eagle Nebula. This happens everywhere, that clouds of interstellar gas get shaped by the ultraviolet flux of these bright stars. You can get these stalagmite type shapes, almost cavities with light shining on. And that's where the new stars are formed. And for exoplanets, you can see in these pillars like here.
Oh,
This is
Roger, are you meaning to share?
Oh, sorry. Yes. Did I not share this? I'm sorry.
Yeah, you stopped
Yeah.
earlier.
Oh, okay. So I'm glad you're telling me that because I didn't realize that. And why did I stop to share? Oh, because I couldn't share them at the same time. Sorry about that. How much did you miss? I start talking about the star cluster and the pillars of creation you can see here, but this is not the Eagle Nebula. This is in a nearby star-forming region. And you can see here that these, well, they're not rendered blue ultraviolet here, but these young stars in this cluster shape these columns of gas and dust. And out of these, can you see this now, Tom?
Yes.
Yeah, out of these, somehow it doesn't tell me what I'm sharing. So you can see the optical image and the infrared, the dark image here at the bottom. And this particular finger, it looks like the finger of ET. You can see all that? Tom?
Yes.
Yeah, okay, good.
Showing.
So in the middle of this cloud, it looks like a big sausage or a bad dog or something. There's a squirt of material that gets squirted out. And if you look in the infrared, you can look past most of the smoke and the dust. You can actually see where the protostar is forming. And in the aftermath of the formation of this protostar right here, these two jets of material get spun out of the disk and move out in the polar directions. And it is there that exoplanets are forming. So a star will form in the middle and a disk of debris material will form surrounding it. And this disk will eventually form Jupiters and Saturns and Neptunes and Earths. And here you can see enlarged in 2004, 2005. This is in the nearby star Fomalhaut. You can see in the southern hemisphere this time of the year, a little earlier in the year, was observed with Hubble. This debris disk was formed. And pieces are moving between 2004 and 2006. So this is a protoplanet that's forming in this disk. And so many of these stars will have planets surrounding them. We think most stars actually do have planets surrounding them. And this one was observed with an earlier infrared camera on Hubble, NICMOS. It's very difficult. You have to subtract the central starlight. But when you do that properly, you can see 3 planets. And if you stare hard, maybe a 4th planet that are orbiting this central star, which is here in this model. So you can actually really be into the business of finding planets around nearby stars, either through direct imaging or even more excitingly, perhaps through spectroscopy. You're all aware of these a transiting exoplanet where a planet goes in front and behind the star. When it goes in front right here, this blue atmosphere planet will, right when it transits in front of the stellar disk and when it exits, the atmosphere will cause this slightly sloped light curve, this U-shaped light curve, which is not like an infinitely steep U, but it's slightly tilted on the sides. It's almost more like a V. And the shape of that V will tell you how much light there is in the atmosphere of this exoplanet. And if you can then also take a spectrum at the same time during this ingress and egress period, you can actually figure out what the content of chemical elements is. And you need to take an infrared spectrum where the blue line is the model that contains water and carbon dioxide. And there's also an ozone line somewhere. And the black line is the data from 28 hours worth of JWST exposure. So in this case, you could convince yourself that that's a planet with carbon dioxide, because the blue model just seems to follow the black data. The data here is simulated, but that's what we expect. So you can tell that the planet has water, carbon dioxide, and if you get lucky, you can also find ozone features. If you can find ozone, you would have signatures for life. Water and carbon dioxide alone, of course, don't do it, but they're certainly good conditions for life. Let's see what other questions do we have. Well, I think, Adrienne, I think I just answered your question as astrobiology field. Yes, it will be possible to detect biosignatures with this. What eventually will be needed is to go down to, and I forgot now where the ozone line is. I think it's around 7,600 angstroms. And James Webb is not quite able to do that. So to see that kind of line with the transiting exoplanets at 7,600 angstrom, the ozone line, you really need to go to this telescope, which, Adriana, you will need to design and build. That's the ATLAS, the Advanced Technology Large Area Space Telescope. Here, I show the same postage stamps as on the first page, but now the telescope mirror diameters. The 6.5 meter James Webb, the 2.4 meter Hubble mirror, which is here, and the 15 meter ATLAS mirror, they're shown at the correct relative size. So if you think James Webb is big, you know, think about a telescope that fills the Sun Devil Stadium in its entirety. That's what it would take to do that, to see biosignatures on nearby planets, nearby exoplanets. But James Webb will give us a first flavor. It will find the chemical elements that are needed for life, but it may not exclusively find signatures of life.
Looks like you have one last question.
What we got? The spectrometer is a GRISM spectrograph, a grating spectrograph really, and so the light gets bounced off this grating, which basically cascades the light down into the detector as a function of wavelength, where the blue light goes in one direction, the red light goes in another direction. And the resolution is about 2700, meaning that you can get to about 0.03% of the speed of light in terms of accuracy. And that's pretty good for a grating spectrograph. Watch the launch in person. Yes, we were going to. We had money to go to French Guiana, Kourou. But due to the pandemic, this will likely not happen. We're not 100% sure, but traveling to South America, we may not be able to do that very safely in this coming year. Other questions, oral questions?
Got a lot of compliments, Roger, in the chat. That's very
well,
nice.
Thank you. I wasn't able to see it all, but
I think that's the last question. Yeah, very exciting times coming up. So
yeah, let's hope that all goes well, that they haven't overlooked anything. I got to tell you, they've spent a fortune to make sure they don't make the same mistakes as Hubble. So we won't have spherical aberration. They may have some other hiccups, nothing that we know of. There's always a few things that don't go quite right after launch, such as, we're a little worried that when you get to L2, where the darkest place in the solar system, away from the sun and the moon, But you have another problem there. If you think about it, it's not the micrometeorites or the dust. You have that too, but we can handle that. It is, you know, we have a thing out there that is all over the sky called the galaxy. And we have one of the shiniest, largest sunshields in the solar system out there, you know, one of these sunshields. And the galaxy light falls on the sunshield, and the light of the object you're interested in is at the end of this telescope tube in this direction. It comes in and you know, bounces off here, primary and secondary, and appears in the doghouse and in the spectrograph or camera. But there's also light coming off the sunshield that can hit the secondary, and under the wrong angles, you can get stray light from the galaxy. And that could create a little havoc. We think we have a good idea how much stray light we get in the shape of the doghouse, but designed such that we only really look in the forward direction. But there may be a little scattered light here and there that we have to deal with. Now, having said that, the sky brightness will be between 7 and 10 magnitudes brighter than what you get on Earth. It's a factor of 1,000 to 10,000 times fainter, I said. I didn't mean to say brighter. You know, 1,000 to 10,000 times fainter than what you have on Earth. So the sky is very dark to begin with. But therefore, if you have any rogue sources of light, such as stray lights or stars, bright stars just outside the field of view, they may create a little havoc that we'll have to deal with. Other questions?
I think that did it, Roger. I'll turn the meeting over to Gordon. Once again, thank you very much for a very informative talk.
Yeah, sure. Thank you, Tom. Thank you, Gordon. Sorry to run a little late, but we had a good audience and excellent questions.
Yeah, we did. And a great presentation. We don't hear much about James Webb, so thank you very much for bringing us up on board, up to the current situation here. Thank you very much.
Well, stay tuned. A year from now, we'll hopefully have a successful launch, knock on wood, and then the rest will be history.
Everybody is going to be turning blue when that thing launches.
Yeah. Oh, yeah. Very blue.
All right, guys. I think that will do it. Now, everybody remember that next month, our meeting is held on the 4th Friday, which is the 23rd of October. So remember that. And until then, we will see you then. I'll give a countdown, and we will conclude this. So, 3, 2, 1, bye.
Take care.